Welcome to Draw the Logic, where we make complex ideas visual. In this video we will build a complete understanding of the transformer, the architecture behind every major language model today. Before transformers, language models relied on recurrent neural networks. An RNN reads tokens one by one, left to right. Every step depends on the previous one. You cannot skip ahead. Three serious problems cannot parallelize training. Long-range dependencies are forgotten, and the entire source sentence must compress into one tiny vector. The transformer solves all three at once. At the highest level, a transformer takes a sequence of tokens and produces another sequence. We start with input tokens, words broken into pieces. Those tokens pass through the transformer, a stack of attention and feed forward layers. The output is a new token sequence, a translation, a summary, or a generated continuation. Computers don't understand words. We must turn them into numbers first. Each word is mapped to an integer token ID from the vocabulary. That ID is then looked up in an embedding table, a large matrix of learned vectors, typically 512 numbers per token. King and queen cluster together. Cat and dog cluster together. The geometry encodes meaning. Attention looks at all tokens simultaneously, without extra information. The model has no concept of word order. Dog bites man, and man bites dog, contain exactly the same tokens, without position info. Pure attention cannot distinguish them. The original transformer uses sinusoidal encodings, sine and cosine functions at many frequencies. Modern models often learn positions directly, but the goal is the same. Give each position a unique fingerprint. Self-attention is the core mechanism that makes transformers powerful. Every token can directly look at every other token. Take, the cat chased the mouse. Let's focus on cat. Self-attention shows that cat attends most strongly to chased. The model learned that verb is the most relevant context. Harder sentence. The cat that chased mouse was hungry. Which animal is hungry? This requires a long-range connection. Self-attention correctly links was hungry to cat across long range. This is exactly what RNNs struggle with. Attention is implemented using 3 vectors per token: query, key, and value. The query asks, "What am I looking for?" represents the current token's request. The key describes, "What information do I offer?" Each token broadcasts its content. The value carries the actual content that will be retrieved if matched. 3 steps. Compare Q against every K for similarity scores. Normalize with softmax into weights. Then compute a weighted blend of the values. The full attention formula is elegantly compact. Let's unpack each part. Attention of Q. K. V equals softmax of Q times K transpose over the square root of D sub K, all multiplied by V. Dot product of Q and K right pointing arrow raw similarity score for every pair. Divide by square root D underscore K, prevents softmax saturation at high dimensions. Softmax right pointing arrow weights that are all positive and sum to 1. Multiply by V right pointing arrow weighted blend of value vectors as output. After the softmax, we get an attention weight matrix. Rows are query positions. Columns are key positions. Each cell shows how strongly a query token attends to a key token. Darker teal means higher attention weight. Here, cat attends most strongly to sat, since that is the verb this subject performs. The color scale shows low to high attention weight. Instead of one attention operation, the transformer runs several in parallel. Each is called a head. Head 1 specializes in syntax, subject, verb, object structure. Head 2 tracks CO reference, which pronoun maps to which noun. Head 3 captures semantic similarity between distant words. All head outputs are concatenated, then projected back to D underscore model. Total compute is the same as one full width head. Each head just uses D underscore model divided by H dimensions. After attention, each token passes through a small feed-forward network. This adds non-linear capacity without mixing tokens. The input is the token vector from multi-head attention. The first linear layer expands the dimension by a factor of 4. A non-linear activation, typically ReLU or the newer SWIGI-LU. The second linear layer projects back to D_model. The output is the enriched token representation. Crucially, the network runs independently at every position. Token mixing happens only in attention, not here. Deep networks are hard to train. Gradients vanish or explode. Two techniques fix this: residual connections and layer normalization. A residual skip connection takes the input and adds it directly to the sublayer output, bypassing the sublayer. This gives gradients a shortcut to flow back through. The addition result is then layer normalized to keep values well behaved. Layer normalization computes mean and standard deviation across features and rescales to unit variance, keeping activation stable in deep stacks. Every sublayer in the transformer uses this same pattern: add and norm. One encoder block contains two sublayers: multi-head self-attention and a feed-forward network, each followed by add and norm. Here is one encoder block. Each sublayer is wrapped in add and norm. The full encoder stacks 6 of these blocks. Early layers learn surface patterns. Later layers build deeper semantics. Each layer enriches the representations passed upward. The decoder has 3 sublayers per block. I will walk through each one. The decoder block is wrapped in the same n-layer repeat. First, masked self-attention lets the decoder attend to its own previous tokens, but not to future ones. Second, cross-attention. The decoder queries the encoder's output. This is how source information flows to the target. Third, a standard feed-forward network, same as the encoder. The encoder output supplies the keys and values for cross-attention. The decoder's current state supplies the queries. When the decoder generates token 4, it must not see tokens 5, 6, or 7. They do not exist yet. The mask is a lower triangular matrix. A green checkmark means the query can attend to that key. Red -infinity means the attention score is forced to 0 after softmax. Row 3-4, at 8, can see all previous tokens, but is completely blind to what follows. During training, masking lets the model predict all output tokens in parallel. During inference, it generates one token at a time. The mask keeps both modes consistent. During training, we use teacher forcing. Correct output tokens are fed in simultaneously under the causal mask. All positions are predicted in parallel, making training very fast. At inference, the model generates one token at a time, feeding each result back as the next input. A key value cache stores past computations to avoid redundant work. Different families use different objectives. GPT predicts the next token. BERT predicts masked tokens. T5 reconstructs corrupted spans. 3 properties make transformers the dominant architecture in AI today. Parallelism. All positions processed at once during training. GPUs love this. Long-range context. Direct token-to-token attention regardless of sequence length. Scale. More data plus more params equals reliably better results. Scaling laws hold. The table is clear. Transformers win on every axis: parallelism, long-range context, and scaling. Tokenize and embed. Words become positional vectors. Self-attention. Every token attends to every other directly. Multi-head. H-parallel heads capture different relationship types. Feed forward. Independent non-linear transform at each position. Add and norm. Residuals and layer norm stabilize deep stacks. Encoder understands the input. Decoder generates the output. The transformer works because attention gives every token direct access to relevant context. And the system scales reliably with more data and compute. If this video helped you understand transformers, please like, share it with anyone learning machine learning, and subscribe to Draw the Logic for more deep dives every week. Thank you for watching.